Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll begin our study of inverse trigonometric functions. So we learned one concept in one of the previous videos, that is, a function f of x defined from the set x to the set y, let's say, is invertible if it is 1-to-1 and onto. This is a principle we learned. I'll just explain this quickly. So you can have functions like this. This would be, for example, the graph of y is equal to x square. And if the function is defined from the set x to the set y, then you can have two elements of x, let's say 1 or 2, both going to the same value a. That is fine. That happens in many functions. In this function, the value of y at x is equal to 1 and minus 1 is the same. Right? But a particular value of x can only take one value of y. You cannot say that the value of this function at x is equal to 1 could be 1 or 2. Right? So there's an asymmetry between y and x when it comes to functions. Two values of x can have the same value of y, but two values of y can never occur at one value of x. One value of x only corresponds to one value of y. That would be saying in this figure that two arrows can have the same endpoint, but they cannot have the same starting point. If you have a set in the domain 3, then 3 cannot go to both c and d. That is not even a valid function. Right. Now, if you are taking the inverse of this function, then it would go from y to x. And if you have, let's say, 1 and 2 both going to a, which means the function is not 1-to-1, then in the inverse of this, you would have a going to both 1 and 2, which is not a valid function. So if this is not 1-to-1, the inverse is not a valid function, which means the inverse does not exist. So the inverse only exists if f is 1-to-1. Also, if f is defined in the domain, let's say 1, 2, 3, 4 and 5, then the value of fx has to be defined for every value in the domain. That is the definition of this domain. Right. So the value of f of x at x is equal to 5 has to be defined. Let's say it's d. Let's say this goes to c, this goes to b. Let's just remove one and add another element f here. Right. So now we see that this function now is not onto. Onto means the range of the function is y. That means every element is y in y is the image of some element in x. But now the element f in y is not the image of any element. So when you take the inverse, you'll have a, b, and they'll go to their own normal values. But when you have f, it will not go to any particular value. And you'll have a point in the domain for which the function's value will not be defined, which means it's not again a valid function. Therefore, a function needs to be 1-to-1, otherwise the inverse does not exist, and a function needs to be onto, otherwise the inverse does not exist. 1-to-1 means different values of x always correspond to different values of y, and onto means that the range of the function is equal to this set y. That means every value of y is taken by some value of x. So let's go to trigonometric functions whose inverse we'll try to study in this chapter. So let's look at Sine X, the simplest trigonometric function. It is defined from r to minus 1, 1. When we say a function f is defined from x to y, this is the domain and this is the set to which it is defined. In these cases, I will write this as range, so we'll make it an onto function, but normally this can be bigger than the range as well, in which case it would not be an onto function. Just a little bit of notation here. Square brackets represent closed intervals, which means the endpoints are included. So minus 1 can be a value of sine x for some x, and 1 can also be the value of sine x for some x. So they both are included, that's why it's a closed interval. Normal brackets represent an open interval in which the endpoints are not included. So sin x is defined from r to minus 1 to 1, which means x can take any value belonging to this set of real numbers. But Sine X will always take a value between -1 to 1. Right. Similarly, I'll just write these now and then for each of the trigonometric functions, and we'll draw the graphs and discuss each and every one of them in detail in a moment when we go through the inverses. Right now I'm just trying to show you the areas in which they are defined. So cos x similarly is defined from r to -1 to 1. Tan x. Now x could be r, except there are some values of x at which tan x is not defined. Tan x is sin x by cos x, so whenever cos x is 0, tan x is infinite. So if we remove those elements from the domain, then the function will be defined everywhere and it will be a proper function. Right. So we remove the domain from tan x at which cos x becomes 0. That means all x such that x is equal to 2n plus 1 pi by 2. And obviously we need to tell that n is a number, so we'll write that n is a member of the set of integers. Right. And where does it go to? It goes to r. Because when x approaches minus pi by 2, tan x approaches minus infinity. When x approaches pi by 2, tan x approaches infinity. And we'll see when we do each of these individually in detail, the graph does indeed take every value between minus infinity to infinity. You talk about cot x. Cot x is cos x by sin x. So it is defined everywhere except wherever sin x is 0. That means all x such that x is equal to n pi for n being a member of the set of integers. And again it goes to r. Right. Now you have cosec x and sec x. Now the domain can be anything except obviously again where the denominator becomes 0. So cosec x is 1 by sin x, so it is defined everywhere except where sin x is 0, which is n pi. Right. So cosec x is defined at r minus x such that x is equal to n pi for n being a member of integers. And where does it go to? So it actually goes to r minus 1, 1. Now this second part takes a little bit of explaining. So before that I'll just write it for sec x as well. Sec x, you can guess the LHS, r minus x such that x is equal to 2n plus 1 pi by 2, where n is an integer, which means wherever cos x is 0, and again it goes to r minus 1, 1. Now let's just look at cosec x. Sec x will become clear. So cosec x is 1 by sin x, and sin x takes a value between -1 and 1. So obviously we know that mod of cosec x has to be greater than 1. Right. So cosec x is between minus infinity and -1, or it is between 1 and infinity. Right. Now these are closed brackets, these are open brackets, that's what I want to discuss. So obviously we remove the range -1 to 1 from the set of real numbers. But if it was a closed bracket, that means the set we removed was the set which included -1 and 1, which means we removed -1 and 1 as well. But actually when sin x is 1, cosec x is exactly equal to 1. And when sin x is -1, cosec x is -1. So cosec x can take a value -1 and it can take a value 1. So if we said r minus square brackets -1 to 1, that would remove everything between -1 to 1 with the endpoints included. But we do not want to remove the endpoints because the endpoints can actually be achieved. Right. So if you wanted to look at it on the number line, it would be like this. The value it can take this value and everything before this, and it can take this value and everything after this. So you will have to remove this interval where the endpoints are not included. Right? If you remove the endpoints as well, then it would become x greater than 1 instead of x greater than equal to 1. Right? So that's why these are open brackets, because we do not want to remove 1 from the range, because cosec x can be 1. We want to remove everything smaller than 1 from the range, because cosec x can never be that. Right. So immediately, the moment I told you about sine x, you should have understood that there's a little bit of a problem when you talk about the inverse, because sine x is a function which goes like this. So obviously you see that different values of x can have the same value of y, which means sine x is not 1 to 1. It is onto because it takes every value between -1 and 1, both of them included. If this was open bracket, then this would not be an onto function, because this would not even be a proper definition, because it would take more values than the set R defined. Right. But at this point, sine x is not 1 to 1. So for example, we know sine of 30 degrees is half, and we know sine of 390 degrees is half. Right. So if you were to calculate the inverse of sine x, which will be denoted by sine inverse of x, right, then sine inverse of x at x is equal to half could be either 30 or it could be 390. That means it will not be a valid function. Right. So sine x as it stands, being defined from R to -1 to 1, is not 1 to 1, so it does not have an inverse. However, we can change it a little bit to make sure it does have an inverse. So now let's look at each of these inverse trigonometric functions in detail. So let's look at sine x first. This is the graph of sine x. This is x, this is y, this is 1, this is -1, this is pi, 2 pi, 3 pi, minus pi, this is pi by 2. Yeah, so you know the curve. Right. So obviously sine x does not have an inverse, because sine x as it stands is defined from R to -1 to 1. Where this is the graph I've drawn, it will extend obviously further behind and further forward. So it is not a 1 to 1 function, so the inverse of this function does not exist. But let's look at a different function now. The function, and we already know that if the range or the domain is different, then it's a different function even if the formula is same. So now we'll restrict the domain of sine x. We'll not let it be R, but we'll make sure that it stays between -pi by 2 and pi by 2. So now how does the graph look? This would be -pi by 2. So basically you take everything between this point and you remove everything else. Right. So now this is not part of it. The function we are talking about now is not even defined in these outside ranges. Right. X now can only take a value between -pi by 2 and pi by 2. Right. Like you could say, for example, y is equal to x squared and x is less than 5. That is a valid function, right? There's no rule that says that x has to lie between -infinity and infinity. It can, but you could restrict x to be less than 5. So for sine x, x belongs to the set of real numbers, but if you wanted to, you could define a new function, which is sine x, going from -pi by 2 to pi by 2 to 1. And in this case, you can see the function. I'll try to draw a better graph of it. So pi by 2 minus pi by 2, 1 minus 1. So this is how it looks like. And now we can see that this function is clearly 1 to 1. Right, because now for every value of x, there is one and only one value of y, right? So this function is both 1 to 1 and it is also onto, because every value between -1 to 1 for y is taken by some value of x between -pi/2 to pi/2. You can see that clearly from the figure. These are close points, by the way. Both of them are included. That's why these are closed brackets. Right. When we define for tan x, these will be open brackets. Right, remember that. So sine x is both 1 to 1 and onto. That means its inverse exists. So this is the first thing we need to know about the inverse of these trigonometric functions, that these trigonometric functions generally are not 1 to 1, and so their inverse does not exist. But you could manipulate their domains and you could restrict their domains in such a way that the function does become 1 to 1 and it should stay onto, in which case the inverse would exist. And if y is equal to sine x, then we know what the inverse of this means. The inverse of this would be a function g such that x is equal to g of y. Right? That is the inverse. If y is equal to f of x, x is g of y. Then g is the inverse of f. And that is written as sine inverse of y. So this is basically it. If y is sine x, then you take sine inverse of both sides. Sine inverse of y is x. Right, and now you can generally, what we try to do is y is the dependent variable and x is the independent variable. So I'm just going to write it as y is equal to sine inverse x. I hope you don't get confused by this. If y is equal to sine x, then x is equal to sine inverse y. So I showed you what this function looks like, sine and then to the power of -1. Right, this is not 1 by sine y, by the way. That would be sine y whole to the power -1. That would be 1 by sine y or cosec y. But this is sine inverse of y. Right. So now we are just talking about this function y is equal to sine inverse x. And where is it defined from? Obviously, it is defined from -1 to 1 to -pi/2 to pi/2. Right. So x now can take any value between -1 and 1, and y will take a value between -pi/2 and pi/2. So remember a few minutes ago I talked about sine 30 is half and sine of 390 degrees is half. So if you were to take sine inverse of half, what would it be? Well, now we know it would be 30, because sine inverse of half has the range which is between -pi/2 and pi/2. So the value of sine inverse half is between -90 and 90, which means it's 30 degrees. No other value between -pi/2 and pi/2 gives sine x half. All the other values of x which gives sine x equal to half lie beyond -pi/2 to pi/2. There is only one value within this interval, which is 30. So this is how we can actually create the inverse. And let me just draw the graph. You can try to plot this graph properly yourself, but I can just show you a simple trick to be able to draw graphs of inverses. You just take the mirror image of the original graph about the line y is equal to x. So you take the mirror image of this line, what will you get? This thing will become, the mirror image will be like this. So we'll have it like this, and we'll have it like this. This would be 1, this would be -1, this would be -pi/2, this would be pi/2. So actually now that we've derived this, I'll just draw this again on a new diagram. So y is equal to sine inverse x goes from -1 to 1 to -pi/2 to pi/2, right, which is the inverse of sine x when we defined it from this domain to this range. The graph is like this. Oh, I'm sorry. So this is -1, this is 1, x, y, this is pi/2, This is minus pi by 2. So what is the value of sine inverse half? You just look at the value half, and the sine inverse of half will come out to be pi by 6 or 30 degrees. We generally talk in terms of radians when we talk about inverse trigonometric equations, inverse trigonometric functions. Right. So this is the graph of the curve y is equal to sine inverse x. Now, before we move on to the other functions, I'll just show you one small property, one peculiar property, which will end up in us having to learn a lot of formulas specifically for inverse functions, because there are some funny results which come about. So, let's say you have y is equal to, let's just use different letters. Let's say you have f is equal to sine x and g is equal to sine inverse x. Right. So generally f is equal to sine x can have a value x between minus infinity and infinity. Right. We artificially restricted it to between minus pi by 2 and pi by 2 to make the function 1 to 1 so that we could have an inverse. Right. So in this case x has to be between minus 1 to 1, but for this x can be anything. Right. So what is the value of g of fx? Right, we've learned how to take compositions. That would be sine inverse of sine x. But now x can be anything belonging to R, because for x belonging to R, sine x is between minus 1 and 1. Right. So I hope you don't get confused by this. There are two functions. One is sine x going from R to minus 1 to 1, and the other is sine x going from minus pi by 2 to pi by 2 to minus 1 to 1. The first function is generally the sine x which you use whenever you're solving a question and nothing is given, but it is not 1 to 1, so the inverse does not exist. The second function has a function whose inverse exists. So generally if someone says sine x, the domain is R. So for this function the domain is R. Now what if x is equal to 390 degrees? Right, I'll just use degrees to for the sake of simplicity. So then g is sine inverse of sine of 390 degrees, that is 1 by 2. But what is sine inverse half? That is 30 degrees. So you actually have the relation that sine inverse of sine of x is not always equal to x. It is equal to x if x is within this nice range of minus pi by 2 to pi by 2. But look at x becoming 390. If x is 390, sine x is half. If sine x is half, sine inverse of half is 30 degrees, which, yes, 30 degrees and 390 degrees technically in trigonometric, from the trigonometric perspective, give the same values, but they are different values of x. One is pi by 6, the other is 2 pi plus pi by 6. Right. So one would be here, the other would be way above this. Right. So you can see some funny properties will come about, and we'll see that in this or the next video, because this is going to be a long topic. But now we'll do each of the other inverse trigonometric ratios individually. But before that, there's one small thing, which is if you look at the function sine x, generally. Now remember what I talked about in the previous video. It's alright to have a function like this, because different values of x can have the same value of y. But you can never have a function like this, because a same value of x cannot correspond to two values of y. So you will never ever see functions like this. In fact, I don't think you would ever probably have seen them in any question you've done. Right. So just if we look at sine x, generally sine x goes from minus infinity to infinity. And if we take the inverse of that about the x-axis, it would look something like this. But then it would go on like this, roughly, right? Now this is not a proper function, I just told you, because what is the value at x is equal to half? It can be pi by 6, or maybe it's 2 pi plus pi by 6. Right, going here. 2 pi plus pi by 6. Maybe it's pi minus pi by 6. It can be that value as well. So if we restrict it to between, let's say, this range and this range, if we restrict it between pi by 2 and minus pi by 2, then it indeed does simply look like this, which can be a function. It just cannot go back like this. Right. However, we do not need to necessarily restrict it between minus pi by 2 to pi by 2. We could actually restrict it between pi by 2 and 3 pi by 2 also if we wanted to. That means in the inverse function, the domain of sine x becomes, instead of restricting it from minus pi by 2 to pi by 2, we could take this value for sine x, and in that case, this would be the function. And again, this is a proper function. This is a function which is 1 to 1 and it is 1 to. We could define from minus 3 pi by 2 to minus pi by 2. So the point is, y is equal to, that was the domain of sine x. So y is equal to sine inverse x goes from, the domain is obviously minus 1 to 1 because sine x takes a value between minus 1 and 1. So this will always be between 1 and minus 1. But the range we defined to be going to minus pi by 2 to pi by 2, that is generally called the principal value branch. Which is generally the branch we'll refer to whenever we talk about sine inverse x. But theoretically, you could define sine inverse x on some other ranges. So for example, there is nothing wrong about the function y is equal to sine inverse x, where x goes from minus 1 to 1, but y goes from pi by 2 to 3 pi by 2. This is what this function would be. It is still a 1 to 1, still an onto function. Right. So you can, so basically we had y is equal to sine x, where we restricted the domain to this interval. And so the range of the inverse function was this interval. If we restricted the domain to another interval, any interval in which it was 1 to 1 and on to, then we could have made an invertible function where the range would have been that interval. So if we never mention anything and we say sine x, we mention the principal value of branch of sine x, in which y is between minus pi by 2 and pi by 2. But there is nothing really wrong about some other functions, right, in which the range is different. So let's look at the other ones now, and we'll just follow the same pattern. We'll first restrict the domain and then we'll see what the graph is like. So cos inverse x. So let's start with cos x. So cos x is again defined from r goes to minus 1 to 1. Right. And the graph of cos x is like this. This is pi by 2, this is minus pi by 2, this is 1, this is minus 1, 0, pi. Now, we could try to restrict the domain of this between minus pi by 2 and pi by 2, just like we did in sine x, but that wouldn't really work, because if you look closely, between minus 1 and pi by 2 and pi by 2, not only is it not 1 to 1, but it is not onto as well, because there is no value between 0 and minus 1 which is taken if we define it to be between minus pi by 2 and pi by 2. So what worked for sine x will not necessarily work for cos x. We can choose another range in which to restrict the domain. So I will not use the word range, that might be misleading. We might restrict it to another interval. So in sine x we restricted this r from minus pi by 2 to pi by 2. In cos x we restrict it from 0 to pi. So this is the function basically. This from 0 to pi. Right. So instead of r, this function is not 1 to 1. If instead of this, so this function does not have an inverse. If instead of this, I talk about a function going from 0 to pi, and the range is between minus 1 and 1, it is a 1 to 1 function, and not only that, but it is an onto function as well. Right, because it takes every value between minus 1 and 1. So if this is cos x, then we can define y is equal to cos inverse of x, where x, so not x, where the domain is between -1 and 1, and the range of this one, now we'll reverse the domain and ranges for the inverse, will be between 0 and pi. So the value of cos inverse x always has to lie between 0 and pi, right? So just to look at the inverse of this function, the graph of the inverse, so we'll take them. There are many ways of finding the graph of the inverse. You could do it explicitly as well. I just find this to be the easiest. So we take the mirror image about this line. So this line pretty much remains the same. So it stays like this. And this line would go like this. Right. So you can see the range of this function is now between 0 and pi, as opposed to between -pi/2 and pi/2 for sine inverse x. And this is 1, and this is -1. So you can see when x is 1, cos inverse of 1 is 0, because cos of 0 is 1. Right. Now again, if we were to invert it a little bit more, we could see that it would go like this. This would go down and this would go up. But then you could define it in other ranges as well. You could restrict the domain of cos x, instead of being 0 to pi, you could restrict it between -pi to 0, or between pi and 2 pi. In any of these intervals of pi, not between -pi/2 to pi/2, but any intervals beginning at an integer value of pi and the interval length of pi, in any such interval, cos x will be 1 to 1, and it will be onto, and you can take the inverse. So again, this is the principal branch, in which the range here is 0 to pi, but you could change the ranges and then it would be some other branch. It would not be the principal value branch. Similarly, let's look at tan x. I'll do tan x, and then I'll do cosec x as well, because it's 1 by sine x. But then sec x and cot x I won't do, because I think you'll be able to figure them out on your own and you can look at any book. But cosec x, if you can see from sine x, then sec x you can get from tan x, and cot x will obviously be the inverse of tan x, right? Sorry, sec x you can get from cos x. Yeah. So for tan x, what do we have? For tan x, the domain is r minus x, such that x is equal to 2n plus 1 pi/2, where n belongs to integers, and it goes from this to r, and this is the graph of tan x. At pi/2 it becomes infinity, 3 pi/2. At all these integer values of pi/2, it becomes asymptotic. So it goes like this, and then it goes like this. It becomes 0 at integer values of pi. And these are just the asymptotes. It never reaches these values. Right, so you can see that it indeed does take every value, the y does indeed take every value between -infinity and infinity, even if we just restrict it to this domain, which is what we will be doing. So right now obviously it's not 1 to 1, because this value of x and this value of x give the same value of y, this value of x and this value of x. So it's not 1 to 1, but if instead of this complicated thing, what if we restrict the domain to between -pi/2 and pi/2? Right, in that case it is 1 to 1, and it is onto as well, because every value between -infinity and infinity is taken. But the difference between this and sine x would be, now the domain would be -pi/2 to pi/2, but it would be an open interval. That's why I've put the normal parentheses here. -pi/2 and pi/2 would not be included, because tan of pi/2 is not defined and tan of -pi/2 is not defined. So obviously this is tan x. That means you will get y is equal to tan inverse x, which goes from R, the domain of this is R, to, sorry, not a square bracket, minus pi by 2 to pi by 2. And what will the graph of sine inverse x looks like? So now it will be asymptotic in the horizontal. This is pi by 2. This is minus pi by 2. So we'll just invert this about y is equal to x. So it will be like this. Right, so it asymptotically reaches pi by 2. Y, x. Again, you could restrict this between minus pi by 2 and 3 pi by 2. That will give you a separate function like this between pi by 2 and 3 pi by 2. So you could either have this or this. This, when you see both these lines, that is not a valid function, obviously. But you could, so this would be the principal value branch of this function. But if you restricted the domain of tan x to some other interval, the range of this would be some other interval, and it would be some other branch of this function. There are an infinite number of branches, all having a range which is an interval of pi. Right. Finally, let's just do sec x. Let's just do cosec x, which is the inverse of sine x. And then sec x and cot x you can look in a book yourself. Cot x is just like tan x, and sec x will just be like cosec x. Right, the relationship will be the same as that of sine and cos. So cosec x is defined from R minus x such that x is equal to n pi for n belonging to integers. I hope you're not confused by all this notation. We've discussed all of this before in relations. And it goes to R minus 1 comma 1. Right, and how does the graph go? So when x approaches 0 from the right, it's infinity. Right. When this becomes pi by 2 or minus pi by 2, so at pi by 2 cosec x is 1, and at minus pi by 2 it's minus 1, and then it goes to infinity. So actually the curve is like this. I'll just write this. So it asymptotically approaches infinity from both sides. After this, it is like this again, because it starts increasing in value again as x increases from pi by 2. But we will restrict it to this branch. Right, we will not draw the other branches. If we restrict it to this branch, that means if we restrict it from minus pi by 2 to pi by 2. Right, but we can't restrict it from minus pi by 2 to pi by 2 because at 0 the value of cosec x is infinite. Right, so minus 0. 0 is the one point which we remove, and it can take the value of pi by 2. Sorry, x can take the value of pi by 2, at which cosec x would be 1. Right, this figure should be drawn a little bit more properly. This is 1. At x is equal to pi by 2, cosec x is 1. So it can take minus pi by 2, it can take pi by 2, it just can't take 0. So we'll have to restrict it within this domain. So then the inverse will be simply y is equal to cosec inverse of x, and that will be defined from, and you can see that because the range is R minus 1 to 1, there is no value of x for which this value is taken. Right. Between these two. No value x for which y lies between these two. So if this is the range, then this function indeed is onto, and it goes to R minus 1 to 1 to minus pi by 2 to pi by 2 minus 0. And the graph is the mirror image about y is equal to x. So it will go something like this. both asymptotic behavior. I'll just draw it a little better. Right, where this is -1, this is 1. So x cannot lie between -1 and 1. It can take any other value, and y can take any value between -infinity to infinity. My mistake. X can take any value between -infinity to infinity. Y can take any value between -π/2 and π/2, but y is never technically 0. Right? It is 0 when x approaches infinity. So I'll just write down the ranges for the other one. For sec inverse of x, we define it from r minus -1 to 1 to 0 to pi minus π/2, and for cot inverse x, we define it from r to 0 to pi. So I'm sure you can try to figure these two out on your own based on the first four. In the next video, we'll look at many properties of the inverse trigonometric functions. Thank you.